let us look at a brief presentation of how we transform stresses from one coordinate xz axis into any other orthogonal axis. So what we do is, suppose I have the state of stress here. You can see x, y and z direction. So on each face you will have one normal stress and two shear stresses. On the x face you have sigma xx, sigma xz or xy or yx, sigma zx. Similarly you have in the y phase sigma y, sigma zy, sigma xy. And on the z phase you will have sigma z. Instead of sigma we should say tau here. This is how we define the stress components at any point. What I would like to do is, now that I know the state of stress on the x and y planes, can I transform to another set of planes? Shall I say call them a normal and tangential? So if here is the element here with sigma x and tau xy on the x face, sigma y and tau yx on the y face, and they are all same on both faces because of equilibrium. If I now take another plane which is inclined at an angle theta, so the normal to the plane AA is inclined at n, and obviously the orthogonal plane is shifted in this direction by the same rotation. That means xy axis is rotated through an angle theta. So if I now try to draw the equilibrium equation for this small element, let's look at it. Here is the element with an angle theta here for the normal. So we have x phase sigma x, y phase sigma y, and of course the shear stresses. And here I have the normal stress sigma n and the shear stress tau n. How do I write the equilibrium equation? The best thing we would do would be to resolve all the forces in the normal direction and in the tangential direction. If I do this, so I'll have sigma normal into area of this element, and find out the components of forces in the same direction. So I will have sigma x into what will be the area? This area is inclined or hypotenuse times cos theta. This one would be in terms of sin theta. And similarly we resolve these forces, which will be area here is delta A into sin theta, because this angle wants area. Or look at this way, if I take this length AB, then this will be AB cos theta and this length will be AB sin theta. If I now resolve into various components, we also have to take the components of the shear stresses. So shear stress into this area. Now if the component here in this direction, I'll have to take cos theta, whereas perpendicular to that would be, I'm summing up the forces in the n along the n axis or normal axis, I get this expression. We also know that if I take moments about the center, the shear stresses will all have to be equal on orthogonal planes. Please remember, if I take moment, sigma x into this area will give me a counterclockwise, this will give you opposite direction. So because moment equilibrium, I get the shear stresses are all equal. So all I'm trying to say is that we resolve the forces into n and tangential directions, and here is how we try to satisfy force equilibrium in the tangential direction. So again I take the same, except now the components will be different based on the orientation there. And if you now simplify, the shear stress on the tangential plane is equal to this expression. Now when you define the principal stresses and principal planes are planes on which there is no shear stress. So if I equate tau and t is equal to 0, can I calculate this angle theta? Please remember, we define principal plane as a plane on which only normal stresses are acting and no shear stresses. So here are the two expressions, and if I am solving for the normal stress is equal to sigma x plus sigma y by 2 plus sigma z minus sigma y by 2 into cos 3 theta plus tau zy into sin 2 theta. And when I'm satisfying the equilibrium this condition that shear stress is 0, you will get the angle at which the plane has to be rotated is equal to half arc tan 2 tau zy. That is the shear stress divided by half the difference in the normal stresses. Once I get this theta p, the plane on which the shear stress are 0, you can substitute the value of theta here, and then you will get the principal stresses sigma 1 and sigma 3. And also you can calculate what will be the maximum shear stress, which is equal to sigma z minus sigma y by 2 whole square plus tau zy square and square root of that. The shear stresses can be positive or negative, and so you have the two directions. And here are the two principal stresses, sigma z plus sigma y by 2 plus or minus the second term within the bracket. If I take the plus term, I get the major principal stress, sigma 1. If I take the minus term, I get the minimum principal stress. So sigma 1 and 3 are given by these two, and the maximum shear stress, as I mentioned, is equal to the expression before, as here given earlier, or you can simplify in terms of the principal stresses, because the shear stress, maximum shear stress is the same any way you take it. So when I want to represent them in the soil, we also realize tension is never allowed in soil because a granular material cannot withstand tension. So they all have to be in the compressive side. We assume as if the vertical stress is the major principal stress and the horizontal plane is the minor principal stress, but in some loading situations they may not be the same. So you have to be careful about assuming that. So let's come to the Mohr circle, where I have plot normal stress in the x direction and shear stress on the y direction. So when I'm looking at the plane here, I have sigma z tau x z. So this will be the z normal stress and this will be the shear stress. On the y plane, this is the normal stress here and the shear stress. Please remember the shear stresses are the same. So I'm taking a simple xy coordinate system. I'm plotting sigma z tau xy. I get a point here. I take sigma y tau xy here, and so I get the vertical plane and the horizontal plane. And I know that Mohr plotted this as a circle. If I know the diameter, I can draw the circle. If I do that, I get the major principal stress here and the minor principal stress. And what is the angle? This is the twice the angle through which we rotate. So 2 theta p is given by tau xy by what is this distance? This is half of sigma z minus sigma y by 2. So I get this as tan 2 theta is tau yz by sigma z minus sigma y by 2. So I can see that if I rotate this plane through a half an angle, I get the principal stresses. We also can calculate the maximum shear stress. Here is a positive one and the negative one, and this is equal to the radius of the Mohr circle. This is sigma 1 minus sigma 3 is the diameter, so half of it is the radius, which is equal to maximum shear stress. This is what we have derived earlier. And if you just take a simple example, sigma z is some 98 times p, a given value. P can be 100 kPa, 200 kPa, whatever it is. Sigma y, tau zy, they are given. And so I can now simply calculate what will be the angle through which we have to rotate, which is equal to half arc tan twice tau zy by sigma z minus sigma y. I substitute, I get theta p is about 14.9 degrees. If I substitute that, now I'll get the principal stresses sigma 1 and 3 is sigma z plus sigma y by 2 plus or minus the term within the square root term. And you can see that in this particular case, the principal stresses are 996 and 754 because the shear stress is a very small value. and the maximum shear stress is 0.121 times P. The second point I wanted to mention was about the stress paths. Suppose we have initial Mohr circle is something like this. The stress point is here. Now we are constructing a 4-story building. So as I keep on adding the building, I'll find that the stress circles keep changing from this one to next one, third, fourth, etc. Instead of drawing so many circles, what I would do is only the stress points. I'll do that, and if I do that, I have A, B, C, D, and I get a stress path. Please remember, here you are plotting sigma and tau, whereas in the stress path space we are plotting P, which is equal to sigma 1 plus sigma 3 by 2, Q is equal to sigma 1 minus sigma 3 by 2, and you can get a simple stress path. And these are the simple ways you can see how the stresses change. When I am applying a load, vertical load, the stress path would be here. When I am excavation, it would be downward to the third quadrant. If the wall is moving away, as in a retaining wall, the stress path would be into the second quadrant. And if you are pushing the wall into the soil, we call the passive case, we get the stress path in the fourth coordinate. First coordinate, second, third, fourth. So you can visualize how the stresses are changing within the stress space, and that tells you how the soil is going to behave. These are some of the examples in which it can keep on changing, and this is one of the most illustrative ones. In nature, the point is here. When you have a retaining wall moving away, if it is trying to reach the active state, you have a very short stress path A to C. If you are pushing the wall towards the soil, you have a stress path which is very long, which means you need large deformations, large stresses to push the wall towards the soil. And these two are called active and passive states. When you study in the next course, retaining walls at pressures, this will be very, very useful.